Good morning, this is Mr. Flint, and today we're going to be working on some select concepts that are going to help us finish up Newton's laws. We're not going to be working through all the concepts that are listed. Like, for example, we need to be going through weight, friction, and springs. But right now, we're just really going to focus on weight, and then when we get time, we'll come back to friction and springs. So let's focus on weight and something we call normal force right now with a couple of problems. So let's look at weight in problem number 1. It says, what is the weight of a 49 kilogram object on a planet with twice the gravitational field as Earth? Alright, let's write out what we know here. What are our givens? What do we know? Well, we know that the mass of the object is 49 kilograms. We also are told that the gravitational field is 2 times that of Earth. Okay, so what does that mean? Well, when we look at our acceleration on Earth, it is not equal to 9.8 meters per second squared. So there's our acceleration due to gravity. Now, if it's 2 times that, we would then expect it to be 19.6 meters per second squared. So 2 times 9.8 would give us 19.6. So that is given to us. So I'm going to cross out this because this is for Earth. Okay, and we're actually not on Earth. We're on another planet that's 2 times Earth. So we've got that acceleration. Okay, so our unknown, what we are looking for is weight. Alright, what is weight? So now we need to find a formula for weight. And we have to remember that weight is actually a force. So we can use our equation for force, which is mass times acceleration. We're really doing this equation here, which is weight, which is a force. Still we have mass, and now we have acceleration due to gravity. So we still have force, we're just calling it weight now. We still have mass, and we still have acceleration. Now that acceleration is going to be 2 times what we normally use, because remember, if we come back here, it told us that it's 2 times that of Earth's acceleration. So let's then substitute and solve this problem. And we'll do that right here. Substitute in some numbers. Well, we don't know weight. We're looking for weight. We have the mass. The mass is 49 kilograms. So let's make a little bit better equal sign there. So equals to 49 kilograms times the acceleration, in this case, is 19.6 meters per second squared. Alright, so then we're going to multiply those two things. Alright, so when we multiply those two numbers, we get our weight being equal to 960.4 newtons. Now, if we pay attention to significant figures, it would probably be 960 newtons here. Okay. Number 2, planet Fritzlar, a 44 kilogram object weighs 176 newtons. What is the acceleration of gravity on Fritzlar? Okay, so let's list out our givens and our unknown again. Our givens, our mass is equal to 44 kilograms. The weight is equal to 176 newtons. What is the acceleration of gravity on Fritzlar? So we need to then figure out acceleration. We don't know that. Alright, so let's come to our equation. And again, we're just going to be using that force equals mass times acceleration equation. But this time, our force is weight. It's that force of gravity on an object, also known as weight. Mass times acceleration due to gravity for that specific planet. So let's substitute in some numbers and solve. Before we do that, I actually want to rearrange this equation to solve for that acceleration first. So I'll do that and then I'll substitute in solve. So weight equals mass times acceleration. Let's get rid of that mass, divide that on both sides, and then we get weight divided by mass is equal to the acceleration, or the acceleration is equal to weight divided by mass right here. So we've got weight divided by mass equals that acceleration. Now let's substitute and solve. We know the weight of the object is 176 newtons divided by 44 kilograms, and that will give us 4 meters per second squared. And we know those units meters per second squared because we're looking for acceleration. Those are the units for acceleration. All right, now number 3. Two movers exert forces of 100 newtons and 150 newtons on a 95 kilogram couch. What normal force does the floor exert on the couch? So let's look at doing a free body drawing a free body diagram for that couch. So we have two movers in this couch here, and they're lifting up on it. Not the best picture in the world, but we've got this mover lifting up and this mover lifting up. So when we do our free body, when we draw that free body diagram, we have this lifter lifting up and this lifter lifting up. But then we also have the couch pushing down. And if we didn't have those lifters lifting up, we still have the floor pushing up on it. So when we do this, so let's pretend like the couch is sitting all by itself, that there is no movers lifting up on this couch. If that's the case, then when we draw that free body diagram, we just have the force of gravity pushing down on it and the normal force pushing up on it. And we've listed out these forces before. Here's our normal force, and here's our force of gravity pulling down on it. Well, we still have, in the next picture, we still have the force of gravity pulling down on it. And we still have the floor pushing upwards on it, but now we also have the force from this lifter and the force from this lifter. So we've got the first lifter and the second lifter here, still now pushing up on the couch. So that's going to actually reduce the normal force. So what we have to do here is we've got to take the sum of all forces is equal to the mass of the couch times the acceleration of the couch in this case. All right, and so we're going to have, so again, we need to use this, the sum of all forces equals the mass times acceleration of the couch. So we're going to have some positive forces here. Let's say that right now the normal force, let's say upward is positive and downward is negative. Okay, and I'm doing that because we're trying to solve for normal force, so I just want to make this force positive. In order to do that, I've got to define upwards as positive. So I can say the normal force plus the force of the first person lifting up plus the force of the second person lifting up. Okay, so we have, again, the normal force, the force of the first person lifting up plus the force of the second person lifting up, minus, in this case I'm going to make this negative because it's downwards, minus the force of gravity. That's equal to ma. Now, if the couch is not moving yet, and it's not, then this has to be 0. So what we're going to end up with, basically, is all the forces on top are going to equal this one force going down, because it's not going anywhere. So we're going to say all the forces on top are going to equal this Fg right here. Okay, so all those are equal to each other. All right, now that we've gotten this far, let's solve for the normal force. Okay, so we can say the normal force then is going to be equal to something here. Well, we need to subtract out this force from this side and move it over here to isolate normal force. So these two cancel out. Subtract F2. These two cancel out, so minus 2. So what that gives us, the normal force is the force of gravity minus F1 minus F2 right here. Okay. So we're almost ready to plug in numbers. The force of gravity is the mass of the couch times the acceleration due to gravity on the couch minus F1 minus F2. Okay, so there we've got a nice equation for this one. Okay, so now that we have that, let's plug in some numbers to it. So we can say, and I'm going to continue in right over here on this side. Okay, the normal force is equal to the mass of the couch, 95, times the acceleration, 9.8. Okay, and then we're going to add in the force of those lifters. So the first one was lifting up with 100 newtons of force, and the second one's lifting up with 150 newtons of force. So 95 times 9.8 gives us 931. 100 plus 150 gives us 250. We add those together, and we get 1,181 newtons of force. Or if we choose to look at some significant digits, we need to keep it to 2. Some people might round it to 1,200 newtons of force. Either way, it's fine. Okay, either way is fine. Okay, so let's go ahead and look at some new problems, and we'll do that in just a second in the next screencast. So we're going to probably do this in 3 parts. So there's part 1. Get ready for parts 2 and 3.